So we'll start with the first tutorial question for chapter 5. Air is flowing at a velocity of 175 meters per second into a 1 meter square inlet of an aircraft engine at 100 kilopascals and 18 degrees Celsius. Compute the volume flow rate in meters cubed per second at the engine's inlet and the mass flow rate in kilograms per second at the engine's outlet. So there we go. So to compute the volumetric flow rate, what we're asking basically is how much, not how much mass of fluid is going through, but given the size of the cross section that it's flowing through, how quickly is it moving through in terms of how much volume of fluid is moving through a given cross section per unit time. So to find out what the volumetric flow rate is, we'll call it V dot. It's a bit too high for me to put the dot, but if we do V dot equals AV, this is just a generic expression for volumetric flow rate. So I'm just going to keep the question open somewhere else. So we're told that the area is 1 meter cubed, 1 meter squared, it's an area, and the velocity is 175 meters per second. So the volumetric flow rate is equal to 175 meters cubed per second. In other words, there are 175 cubic meters of air passing into the engine every second. Now we're also asked to find the mass flow rate at the engine outlet. Now we have, say the engine just looks like a circular duct. We have the inlet and we have the outlet. Now, because we're assuming the mass of fuel being added in the middle is negligible, what that means is that the mass flow rate going through the engine is constant, and whatever's going in is going out. So when they're asking us to find the outlet mass flow rate, they might as well be asking us to find the inlet mass flow rate because they're the same. So the fact that they give us the inlet conditions is all we really need to be able to determine the outlet conditions, which is what they're asking. So what's the difference between volumetric flow rate and mass flow rate? Well, mass flow rate is just the volumetric flow rate multiplied by density. So you get volume multiplied by density, you get mass. So it makes sense that m dot equals rho v dot equals rho a v. Now a and v we know, rho we don't know outright, but we can get it from the ideal gas law, knowing that P equals rho RT, rho equals P over RT. So we can do 100 kilopascals divided by 0.287, which is R for air. And again, we can get that from that first page of the tables if we didn't remember that by heart, and that's okay. And because it's ideal gas law, we're going to use everything in Kelvin. So 18 plus 273 will be our temperature, which is 291. And calculating all of this, we get 1.197 kilograms per meter cubed. Now this is the density of the air as it moves into the engine. Now again, we know the density, we now know everything else we need to know to get the mass flow rate. So m dot equals rho AV, as we saw above over here, 1.197 meters cubed per kilogram. Kilogram per meter cubed. It's the density, not specific volume. Area is 1. And again, velocity hasn't changed. It's 175. So calculating this, we're getting a mass flow rate of 209.54 kilograms per second. So that means every second, any cross-section in the engine, whether it's here, 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 whether it's the inlet or the outlet, which is what's being asked, either way, the amount of mass that passes through any cross-section in 1 second is 209.54 kilograms.